In this video, I am going to discuss hypothesis tests concerning means using Excel 365. So, brief review of what we have seen before when we've done hypothesis testing for proportions and how it differs when we do it for means. Every hypothesis test needs a null hypothesis, H0, and an alternative hypothesis, H1. The null hypothesis is an assumption about the population parameter. It's basically the value of the assumed parameter. The alternative hypothesis will be like a claim if your claim is worded as an inequality. Typically, we will have that claim in terms of a less than or a greater than. So if the claim is that the population mean is less than some value, we use the less than in H1, and it's a left-tailed test. If the claim, however, is a greater than, then H1 will contain the greater than, and it will be a right-tailed test. We also want to choose the significance level alpha, which defines an unlikely probability, and I'm going to keep using 0.025 to denote just one tail when we're looking at the middle 95% to be the likely values. Let's go ahead and start looking at an example. But before we get to the hypothesis test, let's first review the confidence intervals, because we will be using the data analysis tool to get our summary statistics, and then that will aid us in the hypothesis test. So to construct a 95% confidence interval for the mean, we are going to take the sample mean and we will subtract the margin of error to get the left endpoint, and we will take the sample mean and add the margin of error to get the right endpoint. We can quickly find the margin of error using the data analysis tool. So when you go to data, then we are going to go to data analysis. Hold on a second here. Oh, there it is. Don't know why it's all scrunched in there together, but there's the data analysis tool. And we are going to go to Descriptive Statistics. Our input range is all our data. I am going to highlight the first cell, which is the label for our data. So that means I need to click this box to indicate my first row is a label and not a data value. I want to output my data on this same worksheet. So all I need to do is click the upper left corner for the output. So I will put that here in K4. I want to make sure I tell Excel to compute for me all the summary statistics as well as the margin of error. Remember, this output here, confidence level for mean, will give the margin of error for whatever level of confidence you put here. We're doing 95% level of confidence, and this is the default. Once you have all this filled in and selected properly, click OK. And then here's our information, our summary statistics. When we do the confidence interval here, we actually only need two values from the summary statistics. We need the sample mean and we need the margin of error. That margin of error is labeled as confidence level here in the output. So I will make a note next to it that this is the margin of error. So to find the left endpoint, we simply hit equals, click on the mean, and subtract the margin of error. That gives us 2498.34, and we are working on PSI, so that would be PSI. To find the right endpoint, we do the mean plus the margin of error. So the mean plus the margin of error, that gives us 2501.45. These are both in units PSI. So now we're going to write our sentence. And to give me some more room, I'm going to move this out of the way. So I'm going to highlight, hit Control X, and move it down here, enter. So here is our sentence, the interpretation for these endpoints. We are 95% confident that the population mean pressure that could be withstood by concrete, population mean pressure that can be withstood by this concrete. Remember, we're making a claim about the entire population, not just about the 40 samples. So that's why you don't see anything about the samples or the 40. It's about the population mean for this type of concrete. Is between 2498.34 psi and 2501.45 psi. Notice I rounded these to 2 decimal places, or I kept the 2 decimal places that came up here, because all the original data is only to 1 decimal place, and we want to round off our sample statistics and confidence intervals to 2 decimal places, meaning 1 more decimal place than the original data. So here we then find that according to our confidence interval, then we're 95% confident that population mean is somewhere between 2498.34 and 2501.45. Now let's look at a hypothesis test. We want to test the claim that the mean PSI is less than 2502. Notice this upper limit here, this right endpoint, or upper bound, is 2501.45, which is less than 2502. We should get a conclusion that supports this claim, as we see that everything in the interval is less than this value. Let's go ahead and see that if that's the case. So the claim is that our sample mean, the claim is that the population mean of this concrete, or the pressure that this concrete can withstand, is less than 2502. The null hypothesis then is always equality, so it's a claim that the mean is equal to the 2502. The alternative hypothesis is an inequality, so it is the same as the claim that the population mean is less than 2502. And I am going to select the alpha I usually do, 0.025, and this will correspond to the area in the left tail for a 95% confidence interval, so that the result we get for this test should match up with our confidence interval result. Now, when we do a claim about a mean, we are going to use the t-distribution. That means we need our sample statistic, which is the t-statistic. So our sample, I should say our test statistic, my mistake, our test statistic is a t-stat. And this is computed by taking the sample mean, subtracting from it the assumed parameter that is in the null hypothesis, so that would be this 2502, and then dividing it by the standard error. Over here in the intro, I talk about t-stat, and I have here sample statistic, which in this case is the sample mean, minus the assumed parameter, and the value in the null hypothesis is our assumed parameter. Then we divide it by the standard error. When we use a data analysis tool, the standard error is output for us in the second row right here. So we're going to use this. If you did not have the data analysis tool, but you had to compute things independently, you would first find the standard deviation, and then to compute the standard error, you would divide the standard deviation by the square root of the sample size. So let me remind you how that would be done. Going back to example 1, suppose you did not have the standard error here. Then what you could do is you could find the standard deviation by using the formula STDEV.S. So equals STDEV.S of this data set. So let me highlight the data set. And it doesn't matter if you start at A1 or A2. When you have a formula, it will simply ignore non-numerical values in the cells. So the standard deviation A1 to A4, A1 to A41, and there's that 4.86072. If you didn't have this data analysis tool, you would also need to find the mean. And remember, the mean is found using the formula average. So we would go equals average, and I'm just going to type in here A1 colon A41. There's that 2499.9 that you could get if you did not have the data analysis tool. You can then find your standard error by taking the standard deviation we computed here and then divide it by the square root of the sample size, in which case is 40. And there is the 0.76855 that we see here. So this is computed as standard deviation divided by the square root of the sample size. So you can always find the standard error and the sample mean by using the formulas average and standard deviation.s, and then taking that standard deviation and dividing by the square root of the sample size to get the standard error. But since we have this output, we can do it much faster and simply use the output and the value in our null hypothesis to compute our t-stat. So t-stat equals, open parenthesis, the sample mean minus that assumed parameter in the null hypothesis of 2502, and then we'll divide that by the standard error. And here's our t-stat, negative 2.73. We should expect it to be negative because this is a left-tailed test, since we have a less than here in our claim and our alternative is a less than. So this is negative. Also notice it's a bit beyond 2 standard errors from the mean, so this is likely to give us a small p-value, which then would be small as in smaller than alpha, which would reject the null and support the alternative like we're expecting it to do based on our confidence interval we just computed. Now when you're using Excel 365, we can leave this negative, and to find the p-value, we are doing a t-distribution, right? We're using a t-stat for the t-distribution, so we want t.dist, t.dist. The first input x here is the t-stat, which for us is in cell D18. Since I can't click on it, I can type it in D18. Degrees of freedom. This, remember, depends on the sample size because the p-value, which depends on the t-distribution, is different for different sample sizes. The t-distribution takes into account that smaller sample sizes have more variation, so it has to use degrees of freedom to account for that. Degrees of freedom are one less than the sample size, so our degrees of freedom is 39. And whenever we're computing p-values, the cumulative is true. So look here, we have a 0.00462, which is indeed less than alpha. Going back to the intro then, notice our t-stat we discussed, sample statistic minus assumed parameter divided by standard error, or sample mean minus value from the null hypothesis divided by standard error. Degrees of freedom, one less than the sample size, and we're doing a left tail test, so we just need t-dist, where the first input is t-stat, second input is the degrees of freedom, and then the cumulative input is true. If our p-value is less than alpha, we reject the null hypothesis and support the alternative, which then means that the sample data support the claim because the alternative is our claim. So coming back here, we saw our p-value was less than alpha, so we are going to reject the null hypothesis, support the alternative hypothesis. The alternative hypothesis is our claim, so the sample data support the claim that the population mean, PSI, that can be withstood by this concrete is less than 2,502 PSI. So what that means then is the difference between our sample mean, this 2499.9, the difference between the sample mean of 2499.9 and the assumed value of 2502 is statistically significant. It's not likely due to random sampling error, but is statistically significant. So the difference between the sample mean and the assumed parameter, remember this is the value in the null hypothesis, is statistically significant. And so here's an example then of a left tail test for a population mean and how it lined up with the confidence interval. Let's do another example, but this time let's do a right tail test. So we're going to test the claim that the average rating, because here we have ratings for a new bottle design for a popular soft drink, we want to test the claim that the average rating is greater than 30. So this is going to be a greater than and a right tail test. Before we get to that though, let's go ahead and review constructing the confidence interval using the data analysis tool. So let's go to data, my data analysis, descriptive statistics. I have 60 samples this time, so I have to make sure that I have everything in here because now we're going all the way down to 61. I could have just changed the previous 4 to a 6 there. I have my labels in the first row. My output, do I still want it in K4? Actually, I'm going to put it this time in J4. I have my summary statistics and my confidence level for mean, which gives me the margin of error checked. So we click OK. Here is our information. First thing we're going to be using, the sample mean of 30.35, notice, which just is a little bit bigger than 30, and the margin of error here, which is 0.8029. So notice it is a small margin of error. So let's see what we get here. So let's do the left endpoint. So that will be the mean minus the margin of error. Then the right endpoint, which is the mean plus, that was silly, which is, hit the equals, the mean plus the margin of error, enter. Our ratings are whole numbers. We only want our endpoints to be one decimal place more than the original data, so that means it can only have one decimal place. So the left endpoint is a rating of 29.5, the right a rating of 31.2. Okay, now 31.2 is bigger than 30. However, the left endpoint is less than 30. So it does not look like it necessarily, as the population mean is necessarily greater than 30. So I will suspect we will fail to support this claim. Let me go ahead and move this a little bit out of the way so that I can write my sentence. We are 95% confident that the population mean rating is between 29.5 and 31.2. Notice there are no units here, it's just a rating, so we are finished. Between 29.5 and 31.2, not necessarily greater than 30. Let's now do the test. So the claim is that the population mean is greater than 30. So the null hypothesis will be that the mean equals 30. The alternative will be the claim, since the claim is an inequality and it is a greater than, so this is a right-tailed test. As always, I am going to choose my alpha to be 0.025. Now we are ready to compute t-stat, because all I need here is the mean, the sample mean, the standard error, and the assumed value from the null hypothesis. So equals our sample mean minus our assumed value of 30 divided by the standard error, 0.8725. Notice that is much less than 2 standard errors away. So this is going to have a large p-value, and by large we mean greater than alpha. So our p-value, this is a right-tailed test, so you want to use t-dist RT for right-tailed. We're going to use our t-stat, which is in cell D18. Our degrees of freedom, one less than the sample size of 60, so that's 59. And when you do a RT, t-dist RT, notice there's no cumulative input, so you just have these two inputs. 0.19324, which we can see is much greater than alpha. If we go back to the intro here, notice if your p-value is greater than alpha, you do not reject the null hypothesis, or we'll just make it simple and say we support the null hypothesis. And since the null hypothesis is not our claim, the sample data do not support our claim. So support the null hypothesis, and the sample data do not support the claim that the population mean rating is greater than 30. That means that the difference between the sample mean of 30.35 and the assumed value in the null hypothesis is likely due to random sampling error and is not statistically significant. Right? So this time that difference is not statistically significant, so it's likely due to random sampling error. So these examples are the quickest way you can do a hypothesis test using Excel 365 and the data analysis tool. So I hope this video was useful, and thank you for watching.